Right, the third example then. So the diagram shows a sign attached to a point A. It is supported by two light rods. So rods are rigid, not rigid, rigid. That means they could have a tension. They could have a tension, or they could have a negative tension, which would be a thrust. So tension could be positive or negative. With a string or a rope, you can't have a negative tension. It could just be zero and it would go slack. So an example of a rod would be something like a ruler then, which you could compress, you could squeeze, and you can see there'd be a bend in it. Whereas if that was a string, if you stop pulling it tight, it would just go slack. So that's the difference between something like a rod and a string or a rope. The rod AC is horizontal, and the rod AB is at an angle of alpha to the horizontal, where sine alpha is 0.6. The mass of the sign is 12 kilograms. Calculate the forces acting along each rod, indicating clearly whether the rods are in thrust or tension. Well, I've kind of covered that at the top. If we end up with a positive value, we'll be talking tension. A negative value, then the rods would be in thrust. So we could have two different forces working there in each rod, so they wouldn't be equal. We've got a weight acting down, so this time they're giving us the mass, so the weight will be 12 G-newtons. We'll stick with our usual plus y plus x, and they're telling me that sine alpha is 0.6, so they're telling me that 0.6 is the same as 6/10, so that means the hypotenuse is 10, the opposite is 6. This will be the square root of 100 minus 36, which is the square root of 64, which means that's 8. So sine alpha will be 0.6, cos alpha will be 8/10, which is 0.8. So rather than calculating the angle, we can use those values. Right, we're in equilibrium, so forces in equilibrium, therefore the x component sum will be 0, the y component sum will also be 0. So fx, so if I'm taking x to be positive in that direction, I'm going to have minus t1 minus t2 cos alpha equals 0, and my y components will be all negative again because of my crazy choice of axes. So t1 doesn't play a part in it. Minus t2 sine alpha minus 12g equals 0. And I want to work out the values of force acting along each rod, so I want to know T1 and T2. From equation 2, the only unknown I've got is T2. Once I've found T2, I can put it into 1 and work out the corresponding force T1. So from 2, T2 sine alpha equals minus 12g. I'm getting ahead of myself there, I don't know why I've drawn that in there. So T2 sine alpha equals minus 12g. So T2 will be minus 12g over sine alpha, and I know that sine alpha is 0.6 given to us in the question. So minus 12g over 0.6. So I think I've still got g stored as a on my calculator, but if we just want to check, if we do shift and store, it tells us what we've got stored in all our various variables. So a is 9.8. So on my numerator, negative 12a over 0.6, so that's minus 196 newtons. So T2 is thrust. Put that now in 1, and I want T1. So if I take the negative T1 across, I get minus T2 cos alpha. So that would be minus 196 times cos alpha, which we worked out to be 0.8. So minus minus is a plus, so I've just got to do 196 times 0.8, which is 156.8. I've got G in this, so I need to round that to two significant figures, which will be 160 newtons to SF. So tension in T1 is a tension. So rod AC in tension and rod AB in thrust. And you can kind of anticipate that from what's happening there. If that weight is pulling down, then it's sort of pulling away from that one, which will give us that tension, but it's kind of pushing into that one, making that one want to bend, making that the thrust. Okay, so those are the three examples. Each of the questions that I've given you to do are off old WJC exam papers, so they're the sort of level of difficulty that you need to be able to deal with. So hopefully you can have a good crack at those.